I'm Melissa,
I'm Jam.
and I'm a chemist,
And I'm not.
and welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Okay, Jam, I'm really excited about today's episode, but it's also a little bit off the cuff, maybe, is a good way to
Okay.
put it.
Interesting. I was trying before you actually said what you're going to say, just a little bit. I was like, what could it be? What's a word she's going to say? My hypothesis in those milliseconds was scary. That you're going to say it's a little bit scary.
It is kind of scary, actually, because I feel like I didn't get as definitive of an answer as I wanted.
Huh.
And sometimes that's scary to come, even as a chemist with a PhD. I really am committed to giving good information. And sometimes I get scared that maybe it's not the best information, or should I just wait on this until there's more information? But I decided to just bring y'all along with me because it's an interesting topic.
Okay, cool. So it's back, like, here's an interesting question. Here's what we can find out about it right now.
Yes.
Okay.
Exactly. So, or what I can find out about it right now.
Right.
So today's episode is about what happens to hot coffee when it cools down.
Oh,
And it's
classic.
spiraled.
That's so spiraled.
It's inspired by a viral TikTok where a coffee roaster is trying to explain that. Like a girl asked, why does cold brewed coffee taste good or iced coffee taste good, but hot coffee tastes bad when it cools down?
Okay, yeah.
And so he does a thing called stitching where basically you just respond to it and he explains it.
And by the way, guys, she was explaining the TikTok stuff for my benefit. Y'all probably are like, we know how it works, okay?
Right. Jam doesn't know how it works.
I don't know how it works.
Jam's not on the TikTok, which is honestly a blessing because TikTok's kind of a time suck.
And I heard it's on the phone, the phone screens.
Yeah, it's on the phone screens.
Yeah.
So that's where I found it on my little phone screen box.
I kept meaning to look into those. I've heard that they're really cool.
Stop. He does have a phone.
If you're like, how is he, on one hand, like producing this podcast and like editing it and all that stuff, and on the other hand, doesn't even know what a phone is? It's like,
Sometimes I do think I'm just going to get a dumb phone and let it simplify my life a little.
I have considered that too. My younger brother did that for a while.
Did he like it?
He did, and he goes back to it frequently. Like, I mean, depends kind of on the season. There's times where he'll be like, man, I got to go back to my dumb phone.
Yeah.
But, and so I never know. I text him. I don't know until the bubble either turns blue or green when I text him.
That's funny.
And then it's like, oh, okay, it's back to dumb phone. But
Okay, so what this coffee roaster said about why hot coffee tastes bad when it cools down is what he said was essentially there are these molecules called lactones and they break down into acids. And he says a few other things about like the way our taste buds react to different temperatures.
Mhm.
But I heard the part about the lactones breaking down into acids, and at first I was like, that makes sense. That is a reaction that happens. And then I thought, but I'm not sure it would happen in those conditions.
okay.
So I truly spent hours researching this because I couldn't find anywhere in the coffee chemistry or food science world anyone who said the same thing that he said. And the problem is there's a lot of chemistry that looks into different roast temperatures,
Mhm.
but not the different temperatures of the coffee itself. You know, if we roast it this way, what compounds are present? If we roast it this way, what compounds are present?
Mhm.
There was a lot of that, but there was not a lot of same roasting, same brewing method. Let's
Mhm.
watch it as it cools down. There wasn't a lot of that.
So I actually have seen a study that was done. It's kind of funny that, like, obviously once you go into the realm of coffee, there's
Yeah.
a chance that I would see this kind of stuff where it wasn't quite what you're talking about, but it was the idea of the sensory experience for
Yes.
coffee drinkers and what the experience is like and why it's different depending on how the coffee was brewed and what temperature it's being drank at.
Yes.
So cold brew or iced coffee, those different ways of doing that versus hot coffee that's cooled down. And one of the several like different coffee newsletters I received,
Yes.
I saw something about that, which it sounds like it's in a similar thing, but not quite the question you're.
Yes. So I think I saw that same one where it's like hot brew versus cold brew kind of thing.
Yes.
Yeah. So there was a lot on that. I could find like hot brew versus cold brew. And then also, we can talk about this more at the end, but to a degree, the temperature can affect your sensory experiences. So just like
Yeah.
literally your taste buds function differently at different temperatures.
Yeah.
We could talk about that later too. But what those articles looked at was more how the sensory experience changed and not why.
Right.
Really.
Right.
Or there were some that looked at why they were different, the chemistry difference at the molecular level between hot brew and cold brew. But what was specifically hard to find and what specifically I was looking for was hot coffee that had cooled down.
What has happened at the molecular level between those two coffees?
Right.
Yeah,
What's
got it.
going on at the molecular level?
Got it.
And what's hard is when I tried to look this up, what I found was a bunch of articles that were not science articles, like magazine type articles, or I don't know what they're called when they're on the internet.
Yeah.
But that type,
Yeah,
like
yeah.
USA Today or whatever,
Yeah.
quoting the TikTok that I had originally found that I didn't really trust, that I wasn't
Yeah.
sure about.
Right.
So I wanted to share that because I do think it shows how easily a little bit of misinformation can spread.
Yeah.
He shared, okay, this is what, he didn't say think. He was like, this is what happens. And then I thought, I'm not sure, so I'm going to go look that up. And it was really hard to find
Yeah.
anything other than the first layer of the internet was just people quoting him.
Interesting.
Yeah. So this was one episode that I probably spent maybe 4 hours researching for.
Yeah, dang.
I went down a rabbit hole trying to really find what I was looking for. 4 hours maybe researching and pulling everything together.
Wow.
So what he said is lactones break down into acids. And he said into, 2 different types of acids. And that's almost true. Really, lactones and acids will switch back and forth between each other.
Mm-hmm.
It's the idea of an equilibrium. We talked about that idea more in depth on our fluoride episode, if you remember.
Okay. Sounds
It's-
familiar.
Yeah. And lactones are just that's actually sort of a functional group. It's a cyclical compound. It's a ring.
Okay.
They call it a cycle or a cyclic compound. So it can basically open up into like a straight chain. And that straight chain gets some protons added to it, and it's called an acid. So basically it could be closed into the ring. That's a lactone. Open out in a ring, add some protons. There's an acid. And
Okay.
that reaction, this is interesting because it's reacting with itself to
Okay.
make the ring, to open and close it. We haven't talked about the fact that that can happen really, but
Uh-huh.
molecules can react with themselves to become rings.
Interesting.
But in this case, it's sort of like the ring closes and the ring opens up, and that exists in equilibrium. So some of the molecules are closing, some of the molecules are opening. It's sort of going back and forth until there's roughly an even rate of opening and closing happening back and forth.
Okay.
So for more details on that equilibrium, go back and give that fluoride episode a listen. But you can sort of control if you want more of one thing or the other, if you want more of the ring versus more of the open one, you can change conditions. And the thing that confused me a little bit about what he was saying is that in acidic conditions, actually, I think the lactone is favored over the open chain acid.
Okay.
The reason I sort of think of it, although this isn't exactly accurate, I'm like, oh yeah, well, if it's acidic, there's already acid, like in acidic conditions, there's already acid. It doesn't want more acid, so it'll just close up.
Right. I see.
It was hard to find in the specific conditions of coffee if that was true, but
Okay.
that's what gave me a little red flag. So that was my initial, I'm not sure if this is happening, you know?
Yeah.
And so I had to dive deep, like I said, and I couldn't find anything specific that lined up with this idea that lactones break down into acids and make our coffee taste sour.
Mm-hmm.
But what I did find in food science articles was actually the opposite. So in all the food chemistry articles I could find, actually, most people agreed that the progression goes from the acid to the lactone. So from the open chain to a closed chain. And actually, the acid is kind of sour, but the closed chain, it's a specific type of acid, chlorogenic acid, and then it becomes chlorogenic acid lactone, is what it's called, if you've ever heard those terms in the coffee world. The lactone gives this nice, bitter flavor that's like an enjoyable a little bit, a good bitter, is what they called it. But then that can break down even further into something that is a bad bitter flavor.
Okay.
So that's what all of the science articles I could find said, is that he's so close because he's sort of just talking about how basically as it sits out, chemical reactions happen, and this is the one that happens, and that's why our coffee is sour, is because there's more acid present after it cools down. It is true to a degree that as your coffee sits out, chemistry is happening, but it's kind of happening in the opposite direction he talked about.
Yeah.
And the acids aren't usually considered to be bitter. Acids are more considered to be sour.
Right.
There's like, I don't know who started tasting things, but
Yeah.
there's a thing that you can remember, like for acids and bases, and that bases taste bitter and they turn this paper that checks for acidity or basicity blue. So basic is a bigger pH, it's bitter, and it turns the paper blue, and all that starts with B.
Right.
So when he said, like, oh, I think it's more bitter, I think that's part of the thing that I was like, room temperature coffee is more bitter, that shouldn't be more acidic. So I was kind of confused.
Oh, I see. Yeah.
That was just part of that was an aside. That was what kind of put me off originally.
Yeah.
So then I was like, well, what's the thing it breaks down into? And how does that happen? And why does it happen more with hot coffee than like cold brew coffee?
Yeah.
All these questions started swirling around in my mind. Well, guess what? That was even harder to find. But I did find one. It was a lecture. It was a recorded lecture. It was not a peer-reviewed journal article, but it was a lecture recorded with a food chemist who studies coffee.
Okay.
And he couldn't share the exact mechanism due to copyright and funding issues, but he alluded to the idea of a radical reaction. I think we've talked about radical reactions some, but do you remember much about it?
No, I mean, how related is radical reaction to just radicals, period?
Very, very related.
Okay. Is it that something ends up being left with fewer electrons than it wants or needs or something?
That's really close. So a radical is an unpaired electron.
Okay.
Electrons like to be paired up.
Right.
And they kind of counterbalance each other out. So they're much more stable when they come in twos.
Okay.
Like the ants go marching 2 by 2.
Right. Hurrah. Right. Yeah.
Right. Yeah, definitely. So, but if there's only one electron, then it starts wreaking havoc.
Right.
Also why it's called a radical.
Yeah.
And we talked about that in our benzoyl peroxide episode. And I think a few others, like the antioxidant episode. But radical reactions work in 3 steps. They call it initiation, propagation, and termination.
Okay.
So the initiation step, a radical is formed, usually by heat or light.
Okay.
The propagation step is really, I think, what makes radicals so interesting. I feel like maybe we've talked about this on the podcast before, but I also teach it in class. So it's very hard for me to know if I'm like having deja vu because I taught it in class or because I've taught you it before. But the propagation step is where the radical will go find a non-radical molecule and it will scavenge, sort of. It'll steal an electron and make a bond with that.
Yeah.
So imagine I'm a radical. I have 1 electron and you're a bond and you have 2 electrons.
Uh-huh.
That's what a bond is. It's, 2 electrons being shared usually.
Yeah.
So I'll steal one of them. And that means now I'm stable and I'm not a radical anymore, but now you are a radical.
Right.
And so that's why it's called propagation. It's propagating itself. It's continuing to make more radicals as it reacts.
Right.
And then termination is when 2 radicals find each other. But unless we're in really controlled conditions where is a high number of radicals to non-radical species, termination is less likely. You're a lot more likely to come into contact with a regular old molecule than with a radical reaction. Okay. So the way I kind of thought of it was like a domino effect. Like you have a radical and that makes another 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 radical. So like sort of like as the dominoes fall.
Yeah.
So that's a radical reaction.
Okay.
They tend to keep going unless they're in conditions that are designed to go for a certain amount of time and make them stop. And they use radical reactions to make plastics actually and some other polymers. So they can be very useful, but I would say they're a little difficult to control.
Okay.
So as I mentioned, it turns out that the lactones are formed from the acid. And then they break down further into something grosser and bitter in a bad way called phenolindane.
Mm-hmm.
Have you heard of that in the coffee world?
Or if I have, then I didn't remember it. But
okay. It doesn't really matter. It's just another class of molecules. But they're more bitter than even in a bad way, than the lactones and the acid.
Okay.
And these phenylendanes seem to be maybe a newer realization. Like in the last 10 to 15 years, did they say like, oh, phenylendanes appear to be what's making coffee really bitter.
Okay.
And it was hard to get information about these, but I found that lecture with the food chemist. I believe it was Dr. Sarah Marquardt. I'm not sure how to pronounce it, but she had a lecture where she was talking about her research. It was like at a coffee conference. So that was kind of cool to find. And she mentioned that she's been studying these phenylendanes, and she proposed that they may be formed by a radical reaction.
Okay.
And that was the most I could find. So I'm trying to be very transparent about the fact that this was not a peer-reviewed journal article, but it was from a scientist who studies this.
Got it.
So I feel it's a trustworthy source. If I find out, if more information comes out and that's not right, that's fine. But I wanted to bring you along with this chaotic journey with me. So what's significant about the fact that it might go by a radical reaction to make these bitterest compounds is that radical reactions keep going. So if the radical reaction is initiated by heat in the roasting process, that is possibly why roasting for too long makes coffee more bitter.
Right.
Because there's more time for radical reactions, more initiation of radical reactions, and more time for them to propagate. So you get more of these phenylendanes.
Okay.
Then if you think about the way, molecules work after the roasting process, they'll kind of calm down. They're in the bean. There's not a lot of opportunities for the molecules to interact. So reactions don't usually happen as much if you just have like a solid state of something sitting out.
Right.
Because it's just at room temperature, so there's not a lot of energy put into it to move around. But also, it doesn't have a medium to move around in.
Right.
It's like just solid. It's not, can't come into contact with other things very easily.
Right.
So there's less reaction than when your coffee's sitting on the shelf. But if you then brew that coffee by a hot brew method, in my mind, this is totally chemistry off the cuff, but in my mind, what will happen is when you put something in liquid, in a solvent of some kind, and you heat it up, you're adding energy in for the molecules to move around more. You have heat to initiate a radical reaction again, and there's this medium that they're going to interact in. More heat, molecules are moving around more, so you have heat to initiate the reaction, heat to let the molecules move around more, and a medium for the molecules to move around in, which to me made me immediately think, oh, that radical reaction is going to get going again.
Right.
So if we hot brew our coffee and the radical reaction gets going again, then more and more of these bitter compounds are forming.
Got it.
And even, if it's not hot for very long, that's different than if you have a cold brew method.
Right.
Because you'll have a medium for them to move around in, but you're not initiating more because there's not heat.
Right.
And you're not helping the molecules move around faster because there's not heat. In fact, you're making the molecules move around more slowly if you have a cold brew coffee.
Totally.
So I was like, oh, wait, this really makes sense. And then this is where the second thing that comes into play, what you were talking about, that our taste buds actually function differently at different temperatures, where above a certain temperature, we can't taste as well. Literally, we can't taste as many things.
Yes.
And so it's possible that there was a dual action thing happening where we're getting more radical reaction in our hot brewed coffee that is going to make more of these bitter molecules. And then at the same time, as it cools down, it goes into the range where you can taste those bitter molecules really well.
Right. And the being able to taste different temperatures is something that plays in the coffee a lot.
Yeah.
Where when we do like cuppings of new coffees and stuff like that, they say, go ahead and taste it as soon as you can kind of handle the temperature, but make sure you're continuing to taste it as it cools a bit. So you're actually getting a good idea of what the coffee tastes like. None of us drink our entire cup of coffee while it's,
right.
130,
Except Jam,
40 degrees.
who has that fancy cup that keeps it warm.
That's true. But even then, it still kind of changes, which is probably good reasons for that. But
it's probably the reaction continuing to go.
But we talk about that all the time in terms of like, you're not really getting a good idea of the coffee if you're only tasting it at one temperature.
Right.
Because it's constantly changing. But they also often say that the thing about it being that hot is that it's also probably, the beginning is probably the worst or one of the worst times to actually be able to tell
right.
what the coffee really tastes like, because our taste buds just can't do it. And so like a few minutes later is much better. And those things are still there. It's just that we weren't able to taste them
right.
or whatever. So that plays into that world a lot. So at least that part seems like something that the coffee world has understood and gotten that part right so far.
And he did talk about that in the TikTok. And I really, the reason why I'm not referencing the exact one is I don't want this guy to feel bad. I think he probably, he's a coffee roaster by trade. And so that part of the information was correct. And also the idea that as it's sitting out, it's reacting, that's correct too.
Yeah.
But I was like, nobody cares about the exact reaction except for me and my small community of chemists, but that's not right.
Yeah, totally.
Or I guess a better thing is, that doesn't seem right. What thing is, it's so close, but something doesn't quite fit. And so I just wanted to dive into that and try to find the best information that I could about it.
Totally.
And I just realized, since I was talking about that I didn't give credit where credit was due. I recently did a lecture at Baylor University. I have a colleague who works there. She's really nice, Dr. Harridge. And while I was there, a student asked this question and told me about this TikTok, which is what made me go listen. And at first, I was like, oh yeah, that totally makes sense. And then the more I thought about it, the more I was like, wait, hang on.
Yeah.
I have some questions about this. So I wanted to shout out that student, Allison S. She was really excited about it. And I think she even did a project for class about the coffee episodes that we did.
Oh,
so
nice.
she was really nice. And I wanted to shout her out because I would never have found this without her asking that question. So I really appreciated that.
That's awesome.
Anyway, back to what I was saying. So yeah, I think that he was really close. It was close information to have, but I just wanted to take it a step further and dive into this question with all of this science community here.
Yeah.
The other thing I wanted to say was I can see that cold brew coffee, iced and cold brew coffee, wouldn't have this same bitter as it cools down thing happening for two reasons.
Okay.
One, I already mentioned, cold brew coffee won't get the heat into it.
Yeah, in the first place.
Right. So I think that the reaction's just happening slower with cold brew coffee, honestly. It's probably happening as soon as you have the water added. And so the medium, is getting, the molecules are able to move around a little bit more.
Right.
And they're able to interact a little bit more. But it's cold. So it's like you're taking heat out of it. So they're moving less than they would in a hot situation. So that's why I think it lasts longer in the fridge.
Right.
And you're not getting that second heating where the initiation step happens.
Okay.
And there is evidence to back up that cold brew coffee and hot brew coffee have very different molecules present. So that's interesting.
Yeah.
With iced coffee, which is hot coffee brewed onto a cold setting.
Right. So it's immediately being cooled down.
Yep. That immediately slows down the reaction. But also, both of those coffees are served on ice, which takes our taste buds to the other end of the spectrum, also lessening our ability to taste.
Oh, right. Right.
So that's my suspicion is like, well, it being cold, you're taking energy out,
Mhm.
and that means the molecules are moving less. Reactions go slower when they're colder.
Mm-hmm.
I can't I can't think of a time where that's not true, but maybe in general,
Yeah.
if you have less energy, the molecules are moving less, so the reactions aren't able to move, like the molecules aren't moving around as much, so the reactions aren't able to happen as effectively.
Mm-hmm.
But also, it comes into play again with our biology that our taste buds, when it's cold, they are also a little bit less effective, just like when it's hot.
Okay.
So I think those are the two things that make it to where iced coffee and cold brew coffee don't have the same extent of the this is bitter as it cools down experience.
Interesting.
Isn't that?
Yeah, that's crazy. There's so much there.
I know. And I did also want to say this is probably even more complex than I'm making it.
Right.
You know, I tried to boil it down to something that I was pretty confident that it was accurate based on the sources I had, and something that was a teachable chemistry lesson. But there's so many molecules that make up coffee, and there's so many reactions that are probably happening in addition to this one.
Mm-hmm.
And we haven't even fully elucidated this reaction mechanism. So that's why I said it's a little bit of chemistry off the cuff, and it's definitely simplified down.
Yeah.
But I think this is a good, informed idea of what's actually happening when our coffee cools down.
Right. Right.
So, yeah, isn't that fun?
Yeah, that's crazy.
I had a great time. I love a good challenge, and I got really motivated to do this one. So I really, really enjoyed this a lot.
Yeah. And I definitely wondered this myself. I am committed to always finish drinking the cup of coffee, even if it's getting cool. But I also am starting in a much better place where I'm getting some of the best coffee I can get my hands on, which means that even though, yeah, it does taste a little less good when it's gotten down to room temp or something, it doesn't turn bad. It doesn't turn like,
yeah.
But I have had coffee, like say gas station coffee, something like that,
Yeah.
just as an example. Sorry, gas stations. But it's actually kind of better when it's really hot and you can't taste it as well.
Mm-hmm.
And then the cooler it gets, the better, the more you're tasting it. And that's actually, in that case, a bad thing.
Yeah, some coffees actually, they have different compounds. You know, there's so much to the variety and origin and stuff that they taste better when they're a little bit cooled down. Is some of the stuff I was reading, but that was beyond the scope of this episode, so I left it. But I also had the thought that even though the reaction slows way down when you put it in its solid state, it's probably still happening.
Yeah.
So if you freshly roast your coffee and then consume it rapidly after that, which you do, you're much more likely to have less of the radical reactions happening on the shelf.
Right. Right.
You know, so the faster you consume it, the less it goes quote unquote bad by making more of these bitter taste molecules. But also, it seems like there's a little bit of evidence that the bitter molecules might be part of what has a good antioxidant effect. But I didn't get into that because I was like, nope, that's the time, another episode.
Yeah.
So, but they thought the phenylendanes might be part of what makes coffee actually kind of good for your health.
Interesting.
I know.
Huh.
But then I was like, no,
Phenylendanes.
we can't. I can't tell you how many tabs I had open, like trying to get good information. I ended up using, I think, like 15 sources. Let me count.
Oh my gosh.
17 sources I ended up using for this. And I had more than that, but I tried to distill it down only to the ones that actually informed exactly what I was doing.
Right.
So yeah. Do you want to take a stab at telling it back to me?
Sure. Okay. So when we brew a cup of coffee,
Yep.
it's super hot at the beginning.
Mm-hmm.
And when that happened, when we were brewing the coffee, there's lots of energy there. There's lots of things we've just done.
Mm-hmm.
And this radical reaction has started at that point, correct?
It starts when you roast
when
it.
you're roasting, but then we've sort of
Then it kind of slows down.
slowed it down because the beans are at room temp, hanging out in a cupboard.
Yeah, so it might still be happening. I mean, I think it's likely that it's still happening in a
Yeah.
slow way.
We've ramped it up a bunch by introducing a bunch of heat and getting a medium for everything to be moving around in, correct?
Yes. I mean, most chemistry reactions that I do,
Yeah.
we put it on heat.
Right.
A lot of them, like in the lab, we heat them up. There's a
Yeah.
few exceptions, but
Let's just say the heat's on. All right.
heat's on.
The heat is on. And we're brewing this coffee. There's heat. It's ramping up this radical reaction.
Mm-hmm.
And so a bunch of these radicals, these electrons, are bouncing around and they're starting sort of chain reactions everywhere they go, right?
Yeah, so when I think of it, it's like a molecule that for some reason has like one little wayward radical, like one little wayward electron that doesn't have a buddy. And so anywhere it goes, whatever it interacts with, it's going to steal an electron from that and then make another one of itself and steal a reaction from that and make another one of itself. So it's like converting as it goes. I mean, we don't know the whole mechanism, but converting as it goes, lactones into these other things.
Okay. So it's doing that. So when we're first drinking our cup of coffee at the temperature we can start drinking it at, we're mostly, in terms of flavors like that, we're tasting, there's a good amount of acids there. It's this sour, not quite bitter, depending on the way you want to use those words, but like that might be a slightly more accurate way to put it.
So what my understanding is that there's chlorogenic acids that during the roasting process change into lactones. I think there's still chlorogenic acids there.
Right.
But there's a lot of lactones too. And even in the roasting process, you can start to get some of the phenolindane. So it's like the acids are the kind of sour. They're most present when the coffee is green. And then, this is my understanding. And then as it roasts, there's more of the lactones present. And then as it goes beyond the peak roasting time, further roasting or brewing, that's when more of the conversion from the lactones to the phenolindane happens. That was my understanding.
So basically, our cup of coffee already has all three there.
Yes, that was my understanding.
But as the coffee goes from hot to cool, and as more radicals are bouncing around and causing more chain reactions and stuff like that, so that sort of ratio, you could say, is continually changing.
Yep.
Fewer acids, more acids turning into lactones.
Yep.
And then lactones turning into phenolindane.
Yeah, I hope that's how it's pronounced. I could have been saying it wrong this whole time.
It reminds me of this scene in the movie Fletch, which is like an old 80s comedy with Chevy Chase that my family's watched ever since I was a kid, where he is often trying to pretend to be somebody else so he can just get information. He's an investigative journalist. But sometimes he just is not on his toes as well as he should be. And so one of the times he calls somebody, he tried to pretend to be somebody to get some information. And they're like, I'm sorry, and who are you? And he goes, oh, this is Mr. Phenolindane. Phenolindane makes me think of that. Phenolindane.
It could be phenylindanes, not phenylindanes. Like maybe I'm hitting the L too hard, but that's like roughly how it's spelled.
Right.
So,
Right.
Coffee community, come at me, correct me, and that'll be fine.
I mean, sounds like you're coming at them to correct them. So, just kidding.
Yeah, that's true. I feel bad. I've never made such a direct.
No. I'm just kidding. I think it's perfect. I think it's great. So those things are happening.
Yeah.
They've already actually really started in the roasting process. But
yes,
once we've got our cup of coffee and it's cooling, the amounts that are in there at the molecular level of acids to lactones to phenylindanes, that is slowly changing while the cup of coffee is just sitting there.
Yes.
And that would mean, so you take a sip right at the beginning, and then you walk away and forget your cup of coffee, which, even
I do a lot.
Yep. Even I do it. Even though I love coffee, I do that a lot. And then you come back and it tastes very different. A lot of things have continued to react, continue to change. And those are the things that we taste.
Yep.
When we take a sip.
Yes.
And am I missing any of the big things? I didn't go into the like shape of the molecule stuff that you're talking about.
Yeah, that's okay.
Yeah.
Do you want to do a quick review of how radical reactions work, those 3 steps? I think that's good to talk about too, because that part really explains why this reaction keeps going even while it's sort of on your shelf, or why it's sitting out.
Right. So the radical reaction is starting with there being a radical that's bouncing around as an electron on its own.
The first step is how the radical gets formed. Do you remember that?
Nope.
Initiation.
Dang it.
So initiation, that's okay. You don't have to remember everything.
I remember termination.
This is an authentic learning process.
I remember the last one. I remember the one I heard the most recently.
You've gotten a lot of things thrown at you today. So initiation is, it's literally the bond breaking apart. So you have a good bond that's like, 2 electrons being shared, and then heat or light can initiate, depending on what molecule you have, that will break it up they call it a homogeneous break. So each side gets 1 radical.
Okay.
Instead of the 2 electrons being shared. So that's the initiation step.
Okay. Got it. Next one, transubstantiation, right?
No.
Is step 2.
Is that a religious word?
No, I think it's chemistry. Is the step that you'd call going and taking one from another one?
Yeah. Do you remember what it's called? It's a plant word.
Propagation.
Yep. So it just keeps making more of itself.
Yes.
And so if you have several that initiated and several that are reacting, that might seem like, oh, well, you still only have 1 radical because, there's just 1 radical, whatever. But each molecule that was a radical will be changed.
Right.
If I start out as one whole Melissa and I get cut in half, and I'm only half of Melissa, so I still half of Jam, then now I'm a half Melissa, half Jam.
Right.
And then you'll go steal half of whoever you can find, and then you're half Jam, half the other person. And so every molecule along the chain is changed. Every molecule that becomes a radical and is not a radical anymore has been transformed.
It keeps being the musical chairs effect. There keeps being a person without a chair, and then the person without a chair keeps going and looking. They find a different musical chairs. They steal a chair, and then someone in that doesn't have one, and they're moving on.
Yeah,
It never resolves unless something can terminate it, right? And can actually take that extra electron bouncing around, pair it with another one that isn't also taking it away from another one.
Yes,
right?
yeah. If 2 radicals find each other.
Right.
But even that molecule has been changed.
Right.
So it's kind of chaos because every single molecule that has a radical comes out changed. It's not like you escape unscathed because you got another electron. That electron is attached to something.
Right.
So it's like bringing stuff along with it. Maybe a good idea is like a divorce. Divorce is the initiation step. And so now you have 2 single people that are, it's not really they've been severed from something, their family or whatever. And so now if one of those people gets remarried, then now those kids, from each marriage come together and you've got a new family.
Right.
And then if that couple then gets divorced, I don't know.
Yeah.
Then the next group, all the kids are coming together again. So it's like you're not just interacting with just the electrons, you're bringing the molecule that's attached to the radical too.
The history matters. It affects what happens next.
Yeah.
It's not just like we're not talking about just a free electron with no baggage and no history and no whatever.
Probably the splitting a person in half was the best one because it's like half Melissa, half Jam. And then,
there's still some molecules there. There's just okay.
Yeah. So I think that radical reaction is important because the idea that the radical reaction will keep going indefinitely until the unlikely event of it finding another radical, which there's way less radicals than normal intact molecules.
Right.
That's why it keeps going, even though things are cooling down, it can just keep going and going. That type of reaction It doesn't have a natural end point,
Got it.
except for the termination, which is less likely.
Right.
So I think that's important to the idea too.
Got it.
And a good chemistry lesson that type of reaction exists.
Yeah.
A little chemistry lesson for you.
And there's almost nothing we can do about it. I'm just kidding.
Well, you can keep your coffee cold, maybe.
Yeah. I bet in the like chain reaction aspect, even the like trying to get two radicals to find each other. It's like there's so many, like you were saying, there's so many things to react with. It's like, could you get all of these radicals to find other radicals and stop it? Nope. The chaos will continue.
I think what they do is like in labs, they really control the number of initiators that are present. And, like they really try to control the conditions for the reaction so that there is an end point.
Right.
And you can have different molecules that form radicals that are more or less selective, but that's for your OChem 2 class, not for this podcast. Okay, great. Well, that was really fun. I had a great time researching this episode.
Yeah, I think it's interesting. And you had to look at so much stuff.
I did. I looked at so much stuff. I learned a lot. I didn't know about the taste buds thing, so that was fun. It was a good challenge. I enjoyed it, and I enjoyed being able to bring y'all along with me. So, that being said, have you been enjoying anything this week, Jim?
I have been enjoying anything.
Or
this
lately,
week.
I guess, in general.
Yeah.
It doesn't have to just be this week.
Yeah, I have been. Thanks for asking. It'd be sad if I hadn't been enjoying anything at all.
Yeah, that would be a little sad. You're like, I'm not happy with my family.
Yeah. You mentioned this in our Q&R, but I have been waiting to like sort of officially be able to use this in one of our episodes about the fun thing we share at the end of the week or at the end of the episode until it was fully actually operational. But I've been working on getting solar panels on my house for a while now. This like whole process actually started back in May. And finally they have been installed and everything's been checked out and they have been given the okay to be operated, and the power company has connected them to all the stuff that has happened. So many things people had to check and double check, and different stakeholders that needed to like approve stuff. And now we are producing solar power.
Yay! You're producing it. Are you giving it back to the grid if there's overages?
Correct. Yeah.
Wow.
Most days during the day, we'll be producing more than we could use up in the moment. So
here's
we're
a
sending it
question.
to the grid. Yeah.
Does the power company pay you for the electricity you generate?
Yes, they do. And
wow.
it varies from place to place. City of Denton, very solar friendly. They pay me the same amount that I have to pay to use power from them.
Wow.
So it's all equal. So for the most part, it's basically the way it works. So like at nighttime, I have to use the power from the grid. I didn't do the batteries thing. That's a long story, but I didn't do that. We don't need to really here for the most part. So I'm using power from the grid. In the day, I'm producing more energy than I can really use. So I'm selling it to the grid. So basically, I actually produce more, but the way it nets out shakes out in the end of things, I'm actually most of the time producing more than I need. And so I actually don't have to pay the city for energy because I'm selling more to them than I'm buying.
So do you get a check at the end of the month?
Now that I don't know. I don't think so. In fact, my thought is maybe it'll just be credits that stay there.
Oh yeah, so like in the summer or something.
In the summer when I'm using more.
More at night.
Yeah.
So does that mean it's better for you to do things during the day?
That's a good question. I think the way people think about it is more just like across a year kind of thing because seasons are extreme, they change and stuff. But there might be some strategy there. I'm not sure.
Wow, that's amazing. Props to you, Jim. Way to be environmentally loving.
Yeah, it's pretty fun and cool. And I'm actually a nerd, so I like to look at the numbers of like how much we produced and looking at.
Yeah, he texted us the first time they were generating power and sent me a picture of something I've never looked at before. One of those power meters.
Yeah. It was the one of like how much we've generated. So it's funny because it was like 0.000000014. You know?
I was like, wow, that's amazing. And then that was that was it. Very cool.
So that's mine. What about you? What's been with you?
Well, you already heard about this, so this is more for the listeners. So I'm pretty open about the fact that I struggle with ADHD, but something I don't talk about as much, is I also have anxiety and depression that I deal with as well, especially since my mom died. And exercise is a really good way to treat all of those.
Yeah.
But ice skating got to be too expensive and, inflation. And it's a long drive down to where ice skating happens. And we just got a lot of other responsibilities now that I can't make that happen.
Right.
So I knew I needed something to exercise and to help treat my mind and like my mental and emotional and physical, spiritual health, all of that. So I took the plunge and started a kickboxing class.
Nice.
So I have a membership there. I can do unlimited classes a month, and it's much more affordable than ice skating lessons would be, which, I love ice skating, so I'm sad about that. But it's close by. It's like a 5-minute drive from my house, and I can do it every morning to get started with my day.
Nice.
And so I'm really excited about my kickboxing lessons, and I'm hoping it will kind of help me get out of a little rut I've been in lately with my brain and my mental health. So
yeah.
So that's really exciting. Stay tuned for more information about that. I've heard that they do club nights where when it gets dark outside, because it's like windows in the front of the gym, it's dark outside on weeknights now, and they'll do like club music with like flashing lights type thing, or like LEDs or whatever. And I'm like, okay, that sounds really cute and fun, like a party instead of just a workout.
Yeah.
And my first class was really fun. It went by really quickly, and I like learning a new skill and being around other people when I work out. So I'm really excited about that, and I just wanted to tell y'all. So yay.
That's awesome, dude. Good for you. One, it's just fun to try new things. And two, just trying something to see if it'll help, Like a lot of evidence to suggest that it would. But
definitely.
Sometimes we need to shake stuff up. It's like, physical activity has a huge benefit to our physical bodies and our mental health, but also, may need to try something different.
Yeah.
It's like, maybe I've done this for a long time and I'm having a hard time making that work my schedule. Why not change it up?
Try something new. And I used to, even being on campus, you have to walk into campus to work, and you have to, there was a lot of like physical activity built into my day.
Yeah.
But when I switched to remote work, I don't have to go on campus very much now. I mean, I can, but I don't have to.
Yeah.
And so it was hard for me to even leave the house. And this makes me get up and leave the house. And so I'm trying to sort of schedule my day. Like I wake up, I go to kickboxing, I come home to the office instead of come home to home. I get up, have my whole morning routine, and then I go into work.
Yeah.
So I think that will help me have a little bit more structure to my day.
Yeah.
And I think it will be good for my mental health too, get in a routine, see people. So I'm really excited for that.
That's great. Very cool.
Yeah. Well, thanks. Thanks for being excited for me. And thanks for being a coffee lover. I knew you'd be so excited about this episode and all of our listeners. And thanks to Allison for your idea to do this podcast, because I had a great time.
And thank you for teaching us. Thanks for, you can always count on me to be a coffee lover. Be interested in a coffee topic.
I was so excited to tell you. I was like, I can't wait to tell Jam about this.
Just plays right into my, it's like I'm right in the demographic of this. It's like chemistry and coffee overlapping. I'm into it. And I think a lot of our listeners are as well. So if you have an idea like Allison did for a topic of chemistry in everyday life, please reach out to us at chemforyourlife.com. That's chem, F-O-R, your life, to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to patreon.com/chemforyourlife or tap the link in our show notes to join our super cool community of patrons. If you're not able to do that, you can help us by subscribing to your favorite podcast app or rating and writing a review at Apple Podcasts. That also helps us share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson, and Jam Robinson is our producer. This episode was made possible by our financial supporters on Patreon. It means so much to us that you want to help make chemistry accessible for even more people. Those supporters are Avishai B., Bree M., Brian K., Chris and Claire S., Chelsea B., Derek L., Emerson W., Hunter R., Jacob T., Christina G., Lynn S., Melissa P., Nicole C., Stephen B., Shadow, Suzanne S., Sam N., Stephen B., and Timothy P. Thanks again for everything you do to make chemistry for your life happen.
We'd also like to give a special thanks to our team of reviewers who have checked this episode out before publishing. And if you'd like to learn more about today's chemistry lesson, check out the references for this episode on our show notes or on our website.